Hi, and welcome to another online lecture for General Physics 2. This one deals with the topic of magnetic fields from currents. Just to recap where we've come so far in this unit, we briefly looked at magnets and the fact that they have magnetic poles. We've said that the region around a magnet, and in fact within a magnet, can be described in terms of the magnetic field in that area. And then we showed that when you move electrical charges in a magnetic field, in certain orientations, those moving charges experience a force, and that force can deflect the motion of the particles. So we did this with an apparatus in lab where we sent an electron beam and in the presence of a uniform magnetic field, created a circular trajectory for those moving particles. You can also do the same with charges that are moving in a current-carrying wire. If you put that current-carrying wire into a magnetic field, that wire will experience a force due to that magnetic field and move. Well, here we're talking about magnetic fields created from current-carrying wires themselves. And it turns out you can observe, and we've observed in lab, that when you have a current traveling in a wire, it produces a magnetic field. So in the diagram here, there's a current traveling up in this wire that is located there, and there is a magnetic field around that wire, and we can deduce that by putting a series of small compasses around that wire. They all deflect in different directions, but their directions of their compass needle pointing form a circle. Hence, we deduce that there is a magnetic field created by the current-carrying wire itself, and the direction of that field is in a circle around the wire. So previously, we've seen that a current-carrying wire can experience a magnetic force when placed in a magnetic field, and now it seems there's evidence that the wire is creating its own magnetic field. And in fact, this is one way you can think about what's going on. Something else, like a bar magnet, creates a magnetic field. The wire itself, carrying a current, creates a magnetic field. And how those two magnetic fields interact with one another will tell you something about the forces between the field and the current-carrying wire. Ørsted, I want to say Danish scientist, was the first to notice this phenomena when he passed electrical current through a wire in the region of a compass and noticed that there was a magnetic deflection in that region. You can actually predict the direction of that magnetic field by another right-hand rule. This shouldn't be confused with the right-hand rule that we use to calculate the Lorentz Force, which relates the velocity of the particle, the direction of the magnetic field, and the direction of the force. Here, we're simply pointing the thumb of our right hand in the direction of current flow along a wire, and the fingers of that hand curl in the direction of the magnetic field around that wire. You'll get some experience in doing this in a couple of the tutorials that we will work on. So this is called the field right-hand rule. Some places it's called right-hand rule 2. Again, though, you point your thumb in the direction of the current as shown in the diagram right here, and the fingers of your right hand curl in the direction of the magnetic field. Here is again another place where it's advantageous to be left-handed because you don't have to drop the pencil in order to figure out what the direction is if you're writing on an exam or something like that. So Ampere's law is a law which actually predicts the relationship between how strong that magnetic field is and how much current is traveling in a wire. And Ampere's law is always stated in general, but then applied in specific. And so here's how we do Ampere's law. You can construct a path, and it doesn't matter what shape that path is, around a current-carrying wire or multiple current-carrying wires. Again, it doesn't matter. What matters is when you go to do the calculations, how much current is enclosed within the path that you've arbitrarily drawn around one or more current-carrying wires. And so what you end up doing is looking at, here is a very small place of displacement along that path. And so along that path, my displacement is shown here in this direction. The magnetic field at that point doesn't necessarily point in the same direction as the displacement. So here the full magnetic field is at some angle relative to the displacement along that path. There would be a component of that magnetic field that's parallel to the displacement along the path, and there would be another component, which is not shown on this diagram, perpendicular to that displacement. But what we find is that if you add up all of the contributions involving the component of the magnetic field that's parallel to the displacement times the displacement itself, that it ends up being proportional to the amount of current that's enclosed by the loop. And we turn it into an equality by doing what we always do in physics, figuring out what the numerical constant is and what its units are that will relate the two sides of the equation. Some of you have had some calculus in your past and might find this writing of Ampere's law here to be a little awkward. This is the calculus form of writing Ampere's law, where we actually take the dot product of the magnetic field and the infinitesimally small displacement vector, and then we integrate around the closed loop to find out what the enclosed current is, or to relate the enclosed current to the amount of magnetic field. That constant, mu0, mu, the Greek letter mu, is called the permeability of free space, and it has a value of 4 pi times 10 to the minus 7 Tesla meters per ampere. Again, the units of Tesla meters per ampere are simply the units we need to make all of the math on both sides of this equation work out. And typically it's advantageous to actually leave the 4 pi in. I'll show you why momentarily, but the pi part ends up canceling out. So you could actually calculate a number for 4 pi, but the pi often drops out in many of the calculations that we do. So again, this is Ampere's law in general. Any possible closed path you want to take, and then you have to look at the components of the magnetic field that are along the displacement of that path and add them all up, and that will be proportional to the amount of current that's enclosed in the loop. Well, let's make this easier on ourselves. Let's pick a convenient closed path. Hey, let's do a circle, because a circle has the advantage of always being the same distance away from the current carrying wire. So here I'm some radius r away from the current carrying wire. The magnetic field is symbolized with the B, and again I'm thinking about small bits of displacement along the outside of this circle. So I'm starting with the same general approach to Ampere's law, but one of the advantages is if I'm the same distance away from the current carrying wire everywhere around this wire, the magnetic field has the same strength, and we can find that by either using a magnetic field probe and measuring what the magnetic field is at various places around the wire, or placing a compass at those locations and noticing how much time it takes the compass to align with the magnetic field, which is indicative of the field strength. So if the magnetic field is constant in strength everywhere around the edge of this circle, because every point on this circle is the same distance from the wire, the magnetic field can actually pop out of this sum that I'm doing here. And now I'm just left with something that says the sum of all the little tiny displacements around the edge of the circle. Well, the sum of all the little tiny displacements around the edge of the circle is the circumference of the circle, so we can replace that sigma of the delta L's with the circumference of the circle, or 2 pi times the radius of the circle. So now we've massaged Ampere's law into an expression that says if you multiply the strength of the magnetic field by the circumference of the circle, that is found to be equal to the current that's enclosed in that circle times this permeability of free space constant. But it's saying that the magnetic field as well is proportional to the amount of current that's flowing inside there, and this is something else we observe in the lab. If you increase the current, you increase the strength of the magnetic field. We often use Ampere's law to actually write an expression for calculating the magnetic field, and so if we move the 2 pi r over to the other side, we have an expression that predicts what the magnetic field around a current carrying wire will be. It will equal the permeability constant times the amount of current in the wire divided by 2 times pi times the distance you are away from the wire. And so this predicts that the magnetic field strength will drop off as you move further and further away from the current carrying wire. So here's a practice problem to orient yourself to the second right-hand rule again, the second right-hand rule predicts the direction of the magnetic field at each of these points. So we've drawn a three-dimensional axis on a two-dimensional screen. X is directly to the right, Y is up, and you can think of a Z as coming out of the screen, but it's drawn in perspective view here. So if we have current that's moving up along the Y-axis, what's the direction of the magnetic field at any of these points around there? Well, if you wish, I would encourage you to pause the presentation here and see if you can use that field right-hand rule to make the predictions. I'm going to talk through my responses to each of the 3 points that were listed in the question. So if I orient my thumb toward, parallel with this line toward the top of my screen, the fingers on your right hand curl in such a way that when they come around behind that wire and they're in the plane of the screen at point A, your fingers would be pointing towards you, or they would be pointing in the positive Z direction. So the magnetic field at point A is directed in the positive Z direction, which is option 5. At point B, if you continue to curl those fingers around, by the time you curl the fingers around and get over here at point B, your fingers will be pointing toward the right side of the screen. So the magnetic field at point B points in the positive X direction, which is option 1. At point D, which is up here, again, the direction, well, it only shows a small bit of wire here. If we imagine the wire stretches, I find this a little bit easier. When you are curling around that wire, by the time you get to the XY plane right here, your fingers are directed into the screen. So at point D, the magnetic field is directed in the negative Z direction, or option 6. And you can figure out what it is at the other places as well using similar logic. This, of course, brings up another interesting phenomena. Again, I guess interesting is a relative term here, but something that you can see in the lab as well, and that is the logic goes something like this. We know that current-carrying wires feel forces when they're put in magnetic fields. We know that current-carrying wires create magnetic fields themselves. So if you put 2 or more current-carrying wires next to each other, the one wire will create a magnetic field, and the second wire will feel a force from the magnetic field created by the first, and vice versa. And so 2 current-carrying wires will put forces on each other. So let's think a little bit about the possibilities here. Think of the left hand of the screen as being separate from the right hand of the screen. So I'm not thinking of any interactions between the left and the right. But here I have 2 wires on the left of the screen. I have a 3-dimensional coordinate system where the Z direction is toward the top of the screen, the positive Y direction is to the right of the screen, and the X is coming right out of the screen at you, but drawn in perspective view looks something like this. So what happens if I have current that is traveling in the same direction in both of those wires? Well, I need to figure out what direction the magnetic field is due to each of those current-carrying wires at the location of the other wire. So if you start with the right-hand wire and you orient your thumb in the direction of the current in that wire, and you curl your hand around, by the time you reach the plane of the screen, your fingers are pointing towards you or out of the screen, and so the magnetic field over here in the presence of the left-hand wire, due to the right-hand wire, points out of the screen. If we do the same thing for the field at the right-hand wire due to the left-hand wire, again, line your thumb up with the current in the left-hand wire and then curl the fingers of your right hand around. By the time those fingers encounter the plane of the screen, they're pointing into the screen, and so the magnetic field there points into the screen, or in the perspective here, the negative X direction. Now we can think about forces due to those magnetic fields, and so if I look at the left-hand wire, the charge is moving in the upward direction. So here I'm reverting back to right-hand rule 1. My fingers of my right hand are pointing up to the top of the screen in the direction that the current is going. I curl those fingers towards me or away from the screen because that's the direction of the magnetic field created by the right-hand wire, and that leaves my thumb pointing to the right. which means the left-hand wire experiences a force to the right due to the right-hand wire, or due to the field created by the right-hand wire. Newton's third law would tell us what the answer is for the other force, but let's use the Lorentz Force reasoning in right-hand rule 1 to come to the same conclusion. If you look at the right-hand wire now, the current is also directed to the top of the screen, so you orient the fingers of your right hand pointing towards the top of the screen. You curl those fingers of your right hand so that the fingers are pointing into the screen, or in the negative x direction, and you'll note that the thumb on your right hand is now pointing to the left, which is the direction of the force that the right-hand wire experiences due to the magnetic field created by the left-hand wire. The sum of this is that the two wires with current moving in the same direction exert attractive forces on one another. Let's think about the other possibility, that the wires carry currents in the opposite direction. Well, the magnetic field at the location of the left-hand wire due to the right-hand wire will now be into the screen. Again, if you use the second right-hand rule and orient the thumb of your right hand down towards the bottom of the screen, which is the direction of the current in the right-hand wire, curl the fingers on that hand around. When they hit the plane of the screen, they're pointing into the screen or in the negative x direction. The magnetic field at the right-hand wire due to the left-hand wire is going to be the same as it was over here, because the left-hand wire still has current traveling toward the top of the page, so the magnetic field there also points into the page. Now we switch back to the force right-hand rule and think about what the direction of the forces are on each of those wires. If I look at the left-hand wire and I orient the fingers of my hand in the direction of the current, so they're up toward the top of the screen, and then I curl those fingers in the direction of the magnetic field, which is into the plane of the screen, the thumb on my right hand is pointing to the left, and that's the direction of the force on that wire due to the magnetic field created by the other wire. Do the same thing over here with the right-hand wire. Now I've got to turn my right hand around so that the fingers of my right hand can be directed down towards the bottom of the screen. I curl those fingers into the plane of the screen because that's the direction of the magnetic field, and that leaves my thumb pointing to the right, and that's the direction of the force that the right-hand wire experiences due to the magnetic field created by the left-hand wire. So the punchline here is that when I have current moving in opposite directions in two current-carrying wires, they will actually exert repulsive forces on each other. So we can combine two ideas that we have now to actually predict how big those forces are. So here is the current-carrying wire form of the Lorentz Force law, where we multiply the current times the length of the wire times the strength of the magnetic field times the sine of the angle between the direction the current is traveling in and the direction of the magnetic field. But now we're thinking of the magnetic field as being created by another current-carrying wire. So that other current-carrying wire is found by mu0 times the current in the second current-carrying wire divided by 2 pi r, and you can insert that into the first expression where we see B for the magnetic field to find an expression that allows you to calculate the force between two current-carrying wires. Importantly, even though I used I and I here, the one I is in the wire that's feeling the force, and the other wire is in, the other I rather represents the wire that is exerting the field. So this is the currents in both wires. And just like Coulomb's law has Q1, Q2, this form has I1 and I2, and so that is consistent with what we predict with Newton's third law, that the forces will be equal to each other, in magnitude at least. So a conceptual question involving a current-carrying wire scenario, and then we'll do a calculation with the same scenario, putting some numbers in here. But we have a long straight wire that carries a current to the right. Next to the wire we have this square loop that carries a clockwise current. You would obviously have to have some sort of power supply somewhere around this loop, but it's not shown. What direction, if any, is the net force exerted on the loop by the wire? Well, if you orient the thumb of your right hand along the direction of the current traveling through the current carrying wire on top. So my thumb's pointing toward the right of the screen, and then I curl the fingers of my right hand around. When I get below that wire and encounter the plane of the screen, the fingers on my right hand will be pointing into the screen. And what does that mean? It means everywhere here near this loop there will be a magnetic field into the page in the region of that loop. I could draw that with some magnetic field vectors, which would look like little X's to represent vectors that are into the page. That means that along the top of the loop, there is a force because the direction of the current is perpendicular to the direction of the magnetic field that the wire creates. So if I orient the fingers of my hand, now I'm using the force right hand rule, to the right, because that's the direction of the current in the top part of this loop, and then curl those fingers into the screen, which is the direction I figured out was the direction of the magnetic field, my thumb is left pointing up, so that means there is a force in the upward direction on this top segment of the loop due to the other wire here. And we would actually expect that because we just showed on the previous slide that when we have two wires carrying current in the same direction, they exert attractive forces on each other. The right-hand side of the loop, the current is going down, so I orient the fingers of my right hand in the downward direction, and then I curl them into the direction of the screen. So I'm going to flip my hand around to make that happen, curl the fingers into the screen, and the thumb on my right hand is left pointing to the right. Poor choice of words there. The thumb on my right hand points to the right. That's a little better, meaning the force on the right-hand segment of this wire loop is directed to the right. If I do the bottom here, again the magnetic field is still into the page. The current is now to the left. Curling those fingers into the page to align with the magnetic field leaves your thumb pointing to the bottom of the screen. And on the left-hand side of the loop, if you orient the fingers of your right hand up in the direction of the current, then curl them into the direction of the magnetic field, which is into the screen, your thumb is left pointing to the left. So we got an upward force in the top part of the loop, an outward to the right force on the right part of the loop, a downward force on the bottom part of the loop, and a leftward force on the left part of the loop. And it would seem like those would all cancel one another out, but there is in fact a net force exerted on the loop by the wire. By symmetry, the force on the left side and the right side will cancel each other out because they'll be the same strength. But because the magnetic field created by this top current carrying wire is stronger in the region that the top of the loop is sitting in than it is in the region that the bottom of the loop is sitting in, the upward attractive force on the top of the loop is stronger than the downward repulsive force on the bottom of the loop, and that means there is a net force in the upward direction on this loop, which is option 1. A very similar situation here in this sample problem. So we have a long current carrying wire in a square loop, and the square loop is simply chosen because the geometry is the easiest for deducing what numbers we need to perform the calculations. So the only difference here is that we're now given some specifics. This is a square loop that is 1 meter in length on all sides. The bottom of the loop is 1.2 meters away from the large current carrying wire, so we can deduce that the distance here must be 20 centimeters between the top of the loop and that long current carrying wire. And there is 14 amps in the wire on top and 2.5 amps in the wire in the square. So we want to know a number of things. What's the direction of the net force exerted on the loop? Well, that's convenient. We just figured that out in the previous slide. That should be in the upward direction, though we'll reiterate that when we go through the solution. Calculate the magnitude of the net force acting on the loop. If the loop is extended in the horizontal direction, so it's 1 meter high and 2 meters wide, does the net force exerted on the loop increase or decrease, and explain. If the loop is extended instead in the vertical direction, so now it's 2 meters high and 1 meter wide, does the net force exerted on the loop increase or decrease? So let's make that text smaller so we can fit in some scribbling here. I've gone ahead and drawn on this diagram some vectors that represent the magnetic field. So these are these little circles with X's, which represent magnetic field vectors pointing into the page. and those are due to the current carrying wire up here at the top. I've drawn more of them here than I have at the bottom because, again, field line density is a visual representation of how strong the field is at any given point. So the force on the top of the wire, as we previously worked out, is in the upward direction. The force on the bottom part of that loop is in the downward direction. But since the bottom part of the loop is further away from this current carrying wire than the top is, the force on top is greater than the force on the bottom. Using the right-hand rule, the force right-hand rule, we can work out that the force on the right-hand part of the loop is to the right, the left-hand part of the loop is to the left, and since each point on the left-hand part of the loop has an analogous point on the right-hand part of the loop that's the same distance away from this current carrying wire, those two forces would be equal to each other and essentially cancel each other out. So that means the net force is in the upward direction. If we want to calculate the magnitude of that force, we actually have to calculate how big the force is on the top and the bottom sides. Note that it's helpful to think about what's going on before we rush into calculations, because the forces on the right-hand side and the left-hand side won't be zero, but it turns out we don't need to calculate them because of the symmetry of the situation and the fact that they're the same distances away from the large current carrying wire. So we know that the Lorentz force on a current carrying wire is given by the magnitude of the current times the length of the wire times the magnetic field strength times the sine of the angle between the direction the current is flowing and the direction of the magnetic field. In all of the situations in this problem, that angle is going to be 90 degrees because the magnetic field is into the page and the currents are traveling in the plane of the page. But we're going to use the magnetic field due to a current carrying wire expression that we deduced from Ampere's law in the place of the magnetic field in this expression. So we get this rather larger equation that says the force felt is equal to the current traveling in the loop times the length of whatever side of the loop we're looking at times the permeability constant here times the current traveling in the long straight wire up top divided by 2 pi. R is the distance between the two wires at the given side that we're investigating, and again sine of theta would relate the angle of the current in the loop to the direction of the magnetic field. So at the top, let's see, the loop has 2.5 amps of current. The loop is 1 meter square on each side. The constant is 4 pi times 10 to the minus 7 Tesla meters per ampere. The current from the top straight wire is 14 amps. The angle is 90 degrees, so the sine of theta just gives you 1 in that expression, divided by 2 pi in the denominator times the distance. And again, if the bottom of the loop is 1.2 meters away and the loop is 1 meter square, that must mean the top of the loop is 0.2 meters away from the 14 amp wire. Notice I said that it's helpful to sometimes keep the pi's in, because notice in this case the pi's are going to cancel out, so I don't even need to punch pi in my calculator. They're going to drop out and cancel one another out. If you crunch all of the numbers on there, you find 3.5 times 10 to the negative 5th newtons. If you do the same thing for the bottom, the only thing that changes in the calculation is now you're 1.2 meters away rather than 0.2 meters away, and so that means the force is much weaker. It is 5.8 times 10 to the minus 6 newtons, and the net force is the difference between the two, so it is 2.9 times 10 to the minus 5th newtons. If you take the top minus the bottom, we previously ascertained the direction to be up. If we make the loop wider, what does that do to the net force? It actually is going to increase the net force. You can think about it this way. If we doubled the width of the loop, which I guess is the scenario that it presents, that'll make the force upward twice as big. That'll make the force downward twice as big. But that'll make the net force twice as big as well. So the net force exerted on the loop increases. If you extend the loop in the vertical direction, the answer is actually a little bit ambiguous, because which way do you extend it? If you stretch the bottom part of the loop down so that it is now 2.2 meters away from the 14 amp wire, then you can answer definitively that that will make the bottom force smaller while keeping the top force the same, and that has the effect of increasing the net force, and that's what I thought of in this particular scenario. However, you could imagine stretching the top wire so that the top wire now extended over that 14 amp wire into the region here at the top of the screen, and now the direction of the force on the top part of the wire would be in the downward direction, and depending on how far away you were, it might increase or it might decrease the net force. So you need a little bit more specifics, but if we assume that the bottom of the wire loop is what's stretched downward, that will decrease the net force, or that will rather increase the net force by decreasing the force on the bottom part of that loop. So we can find magnetic fields a number of ways. We've talked about how Ampere's law can be used to find a relationship for predicting the magnetic field created by a current carrying wire at a distance r away from that wire. I'm not going to show in this presentation, but I'm just going to give you the relationships for some other common geometries. Here is one for a loop of wire. If you have a loop of wire and you're at some point along an axis that passes through the middle of that loop. Here the radius of the loop is abbreviated A, and the distance you are away on this point from a point on that loop is given the symbol R. We find that the magnetic field due to that loop is equal to the constant, mu0 again, times the current traveling in that loop, times A squared over 2R cubed. And if you move this point so that you're sitting right in the center of the loop, well then A equals R, and when that happens, then the magnetic field right at the center of a current carrying loop of wire is mu0I over 2R. If you have a whole series of loops, but they have significant length to them, we call this arrangement a solenoid. And for a solenoid, it turns out to just depend on how many turns you have, how much current you have traveling through there, and the length of the arrangement. So this figure shows a Helmholtz coil, which is what you used in the lab when you turned on those coils and deflected the electron beam in a circle. So a Helmholtz coil is two identical circular coils that have the same axis, and they're separated by a distance that's equal to the radius of each coil. This produces a magnetic field that's pretty uniform over the region inside those coils, and so we use this a lot when we need uniform magnetic fields in experimental research. So we want to find what the magnetic field is at this center point P, if we know some things about the coils, such as their radius and how many turns of wire are in each coil and what kind of current we're pumping through those coils. So to do that, we can use the expression for the magnetic field due to a loop. Here I'm assuming the coils are fairly tightly packed together so that I'm not worried about their particular length, whereas in a solenoid I am worried about how stretched out those coils are lengthwise. So we have this expression where the magnetic field from the loop is equal to the number of turns in the loop times the constant times the current traveling in the loop times the square of the radius of the loop over 2 times the distance to the point cubed. And here again, A in this formula is the radius, and R in this formula is the distance from point P out to some point on the loop. So we got to do a little bit of work to figure out what that is. This would be a triangle right here that would have one side that would be R long, the other side would be R over 2 long, and so Pythagorean formula, we'd say R squared plus R over 2 squared gives me R squared plus 1/4 R squared. That's 5/4 R squared, and therefore R, or the distance out to point P, is 5/4 R squared to the 1/2 power, or the square root of 5/4 R squared. So we can work out what the magnetic field is from one of the coils using this loop arrangement. So the number of turns in one of those coils is 36. Here is my constant, 4 pi times 10 to the minus 7 Tesla meters per ampere. 4 amps of current is the current flowing in this system. The radius of the system is 33 centimeters, so 0.33 meters squared, divided by 2 times, and then here's my expression for the distance, 5/4 r squared to the 1/2 power, and then that's all cubed, so it ends up being 5/4 r squared to the 3/2 power. If you crunch all those numbers correctly on your calculator, you work out 1.96 times 10 to the minus 4 Teslas, or let's see, what would that be? 0.196 milliteslas, which is not an incredibly strong magnetic field created by this arrangement. Now, a second coil, then, we would do the calculation for the second coil, but since the second coil is the same distance from point P as the first, the current can be sent through the second coil in such a way that it cancels out the magnetic field from the other one, which wouldn't be that useful if we're trying to build a magnetic field for the lab. Or we could send it in the same direction so that its magnetic field is in the same direction as the magnetic field from the first coil, and this would double the field. That's what we want to have happen, so the overall magnetic field for this Helmholtz coil arrangement would be about 3.92 times 10 to the minus 4 Teslas. So this concludes the presentation on creating magnetic fields from currents. If you've noticed any errors in the presentation, I appreciate you pointing those out, and we'll hope that this is a helpful resource for you learning about electromagnetism.